This screencast discuss how to calculate that equilibrium constant, or the KSP, for a slightly soluble salt. So we have here given the molar solubility of aluminum hydroxide is 2.9 times 10 to the negative 9 molar. That means only this much of however much solid we're going to get will dissolve, that many moles per liter of water that we have. So we're going to use that and an icebox to help us figure out what the KSP values are for aluminum hydroxide, at least at this particular temperature. So it's always good to start with an ionization equation, and that is going to break down. It'll also be at equilibrium for a saturated solution, and 3 hydroxide ions. These are an aqueous solution, and this is a solid. So ICE. Doesn't really matter how much of these we have. We don't include solids into our equilibrium expression anyway. But we know that only this much is going to be dissolved. So at the beginning, we would have no ions, and we know that this much is going to split up. So that means, since there's a 1-to-1 mole ratio of aluminum hydroxide to aluminum, I'm going to get 2.9 times 10 to the negative 9 molar of this in solution of aluminum ions. It's going to give me 3 times, and that's my change. So to translate it over here, it's going to be 3 times that amount, 2.9 times 10 to the negative 9. Oops, that's next. All right, so at equilibrium, I'm going to have 2.9 times 10 to the negative 9 molar of that, and 8.7 times 10 to the negative 9 molar of my hydroxide ions. So what I need to do next is write my equilibrium expression, my KSP, and that's going to be Al3 plus times the concentration of hydroxide ions raised to that power, or their coefficient power. In this case, the coefficient is 3. Now that I have my equilibrium expressions, or my equilibrium concentrations, I'm going to plug those in to find my equilibrium constant value. So this is going to be 2.9 times 10 to the negative 9 times the amount of hydroxide times 10 to the negative 9, and that is cubed. When I multiply those together, I end up with 1.9 times 10 to the negative 33, and that is the KSP for aluminum hydroxide at that temperature. This next problem is very similar. We're still going to be calculating KSP, but this time we are not given the molar solubility. We're given the solubility in milligrams per liter. So we have iron 2 oxalate here, and it is 65.9 milligrams will dissolve in 1 liter. So really, all I really need to do is change these milligrams to moles. Easy enough. So milligram, there are 1,000 milligrams in 1 gram. Now I can change grams to moles using molar mass. And I got the molar mass of iron 2 oxalate to be this. Alright, grams cancel out. And so everything on top multiplied together, I end up with 4.58 times 10 to the negative 4 moles per liter. So now I have that molarity that I started with in this problem. Alright, and now the problem's pretty much the same. It's always good to have a nice balanced equation. I'll move this up. So FeC2O4 is going to split up and be at equilibrium. Iron 2 ions, and then our oxalate ions. And these are both in aqueous solution. Alright, set up our icebox. Solids we don't really have to worry about. So at the beginning we have no ions, and now we know that this much is the only amount that's going to split up into ions. And so we look for our 1-to-1 mole ratio is here. So that's going to be 4.58 times 10 to the negative 4. If that's my change here, then that's how many ions of this I'm going to get as well, since these are at a 1-to-1 mole ratio. And so it's 4.58 times 10 to the negative 4. Now, I can go back, write my equilibrium expression. It only involves those ions because the other is a solid. Both of these are raised to the first power, so we don't have to worry about that, and so it's just plugging in the numbers. So the concentration at equilibrium is 4.58 times 10 to the negative 4 for iron 2. It is the same thing in this case for oxalate. And then we multiply those together, and I get a KSP value of 2.10 times 10 to the negative 7. And that's my answer. Oops.